A lot of quantities in ionizing radiation require us to understand huge scales of length and time, energies from milli-electron volts to mega-electron volts that's spanning 9 orders of magnitude, and times ranging from femtoseconds to gigaseconds, or years in other words. In order to visualize this much information in one place, we use a tool called logarithmic scales, or log scales for short. They're great ways of visualizing tons of information because they turn exponentially large or small numbers into something human readable on a single graph. And specifically, they're good for condensing many orders of magnitude into one graph or picture. Let's show you an example unrelated to ionizing radiation. If we were to look at the processing power or compute power of computers going back from about 1975 to today, and graph it on a regular linear scale, where on the x-axis we have the year, and on the y-axis we have MIPS, or millions of instructions per second, you can see a graph that looks like it's exponentially increasing, and that's because it is. The problem with this graph is that for numbers before about 1992, it's awfully difficult to see what they are. They're slammed all the way down on the x-axis, and if I asked you, well, what was the average MIPS of a computer back in 1975, you'd be hard-pressed to tell me. Instead, we can switch the y-axis from a linear scale to a logarithmic scale. It's a different way of representing the same information. In fact, if we put these two graphs side by side, you'll see that the ranges of MIPS go from about 0 to about 1,000, but on the log scale, every single tick mark is a factor of 10. So each tick mark represents an order of magnitude. And what you might notice here is that all the information fits really cleanly on one graph. So if I asked you what was the average MIPS of a computer in 1975, you'd be able to read off something like 0.05. And if I said, okay, now repeat for 20 years later, you could read that it's about 1,000. So this is a really useful tool for visualizing huge amounts of information, and especially very disparate orders of magnitude. So I put together a little animation to talk about different units of radiation dose, and to visually show you in a zooming in, zooming out kind of scale how disparate dose numbers are. For example, we could talk about the dose you get from eating one banana versus the dose you'd need to statistically cause cancer. And these are off by a factor of 1,000,000. If we tried to graph something on a linear scale, which differed by a factor of 1,000,000, you simply wouldn't be able to see all the points on that graph. And it brings up another interesting question, which is going to be the central theme of today's module. What these log scales will help us answer is when someone says, is radiation dangerous, you can answer how much. So let's say this box represents a sievert of radiation. We zoom in by a factor of 1,000, and another factor of 1,000, and another factor of 10. We get to the dose you get from eating one banana, close to the dose you get from spending a day next to another person. If we zoom out by a factor of 10, we're now in the microsievert regime. Multiply by 5, and you get the dose for a dental x-ray. Multiply by 8, you get the dose from flying across the US. Multiply by about 2, living in a brick building for a year. Multiply by another factor of 2 or so, and you get the dose from eating 1,000 bananas, 1,000 times bigger than that one. Zoom out again and you get a millisievert, which is a lot of radiation. Let's say now you get a normal yearly background dose of 5 millisieverts. And finally, the lowest radiation dose proven to cause cancer is that box right there, from eating 1,000,000 bananas. Now to get all this information on a graph would be kind of difficult. As you can see on this screen, the box representing 1,000,000 bananas worth of dose is visible, but you can't even see the single banana anymore. Yet radiation scientists have to represent this much information on a compact, easy-to-read graph very often. To turn to another example, let's turn to quantifying the likelihood of another useful nuclear reaction from something called boron-neutron capture therapy, or the intentional capture of neutrons by boron to treat cancer. So this is our first introduction to a useful medical procedure using radiation. I'm going to define a quick unit called a barn, which is the unit of a cross-section, or in English, the probability that a nuclear reaction will occur as a function of incoming particle energy. We have to graph this energy over the full range of possible neutron energies in a reactor, which ranges from a little MeV, or a milli-electron volt, all the way to about 10 MeV, or million electron volts. Just to give you a quick refresh, here's the nuclear reaction for boron-neutron capture therapy. In this case, some boron-10, containing 5 protons and 5 neutrons, absorbs a neutron and splits into a lithium atom, an alpha particle, and quite a bit of energy, with that energy being imparted to the lithium atom and the alpha particle as we derived on the light board in the transfer of momentum and energy equation. But now we can ask another question about this reaction. What energy neutron should we use to maximize the effectiveness of this treatment? For that, we can turn to the graph of neutron cross-sections. So shown here is a graph on a linear scale of the incoming neutron energy on the x-axis versus the likelihood of that reaction on the y-axis. Notice you can't see anything. That's because a lot of this information, or the change in this information, happens at very low energies. And using this linear x-axis scale, we can't see anything. In fact, if you look really carefully, you can see a blue line all the way on the left side of the graph. All the information of what happens at low energies is crammed into the y-axis of this graph. If we now switch to a logarithmic axis in y, in cross-section, you can see that the picture is getting a little bit more interesting. There's clearly some variation in cross-section as a function of incoming neutron energy. But again, you can see that there's a lot of information slammed onto the y-axis that we can't see because we can't actually visualize what's going on at these lower energies. If we instead make the x-axis logarithmic and the y-axis linear, all of a sudden the patterns appear to reveal themselves. Where at very high energies, not much change happens, and at very low energies, the neutron cross-section increases greatly. What this tells us is we want to use low-energy neutrons because they're much more likely to be captured by the boron and undergo the effective treatment. If we make both axes logarithmic, now we can see the full range of variability across all energy scales on the x-axis and across all cross-section scales on the y-axis. We can see that there is some variation at high energies, like 1 to 10 MeV, but it's kind of inconsequential because the cross-section, or the probability of that nuclear reaction, is pretty low. And now we can see that this probability of the nuclear reaction to happen keeps on increasing exponentially with decreasing energy, which makes it look like a flat line on this log-log plot, which is the short for a logarithmic x-axis and a logarithmic y-axis. To help you with one little bit of reading a log scale, I want to zoom in on one part of this graph and show you that on a log scale, the tick marks, which represent linear changes in dose, aren't at the same spacing on this particular graph. If I highlight and show you where the y-axis tick marks are, you can see that they start off pretty wide and get narrower and narrower as you get towards some factor of 10. On this graph, we have markers for 1,000, 10,000, and 50,000. And you can see that as these markings get closer and closer to a certain order of magnitude, whichever one it is, they get closer and closer on the graph. This helps you read off much more accurately logarithmically increasing or decreasing values of this cross-section. And if I show you the tick marks on the x-axis, you can see the same things happening here. Once we get to 10 millielectron volts or 100 millielectron volts or even 1 electron volt, the tick marks get closer and closer until you reach an order of magnitude, and then they start expanding again, because the stuff on the right of the graph is 10 times bigger than the stuff on the left of the graph, and so on and so on and so on. And so hopefully this helps you realize how much information you can cram into a single sheet of paper using logarithmic axes. And we'll be describing units of dose and how much dose you can get from smoking, from background radiation, from radon, using these logarithmic scales, either visually in one dimension or in 2 dimensions.